Welcome to Fitting Lines. Our objectives today are to understand that linear patterns can be modeled by linear functions. Also, we will fit a line to a near linear pattern and find a rule. And then we will use those rules, or linear models, to make some predictions. Let's look at our first example. This is about shadows. On sunny days, every vertical object casts a shadow that is related to its height. The following graph shows data from measurements of flag height and shadow location, taken as a flag was raised up its pole. As the flag was raised higher, the location of its shadow moved farther from the base of the pole. Although the points do not all lie on a straight line, the data pattern can be closely approximated by a line. So look at our data. Look at our points. Our independent variable is our flag height. That's what we control. We're raising the flag to different heights, starting from 0 all the way up beyond 20 feet. The y-axis, our dependent variable, is our shadow location. So remember what this says. As we raise the flag up the flagpole, the location of its shadow moves farther from the base of the pole. And here you can see a little bit what that looks like. So here's our flag about halfway up, and here's our shadow. What's going to happen as this flag gets higher and higher? This shadow of the flag will get farther and farther from the base of the pole. This data in this graph represents what we just talked about. So how can we find a line that fits the data pattern closely? Well, if we look here, we notice that these points do not all fall in a straight line, but there's definitely a pattern. There's a trend in the data, and so we can represent this by drawing in a straight line. The question is, where do we draw the line? Do we try to fit as many points as possible to the line? Do we try to find an average? Well, the best way to do it is to find an average. That way, as we go up, some of the outliers, the points that are really high or really low, will be taken into account as far as an average goes. And we won't have to adjust our line to move up through a certain point or down through a certain point. It'll be more accurate if we take an average. In order to do that, it looks like the points will start from around 0, and then we would just draw our line so that we had the same number of points on the right and distance from the line as the points on the left and their distance from the line. So something like that could be pretty close. Now what we want to do is write the rule for a function that has this line as the graph. Remember from a previous lesson, in order to write a rule, we need to find the average rate of change that represents this line. So we need to pick 2 points that are on crosshairs and find the slope. Well, it looks like right here we have 1 point that's right in the crosshairs. If I move up the line, right about here is another point. So if we just count, this starts at 2 and it goes up to 4. That's a distance of 2 feet. Right here is 6, and if we move over to this point, this is 12. That's a distance of 6 feet. So remember, our slope is rise over run, or 2 over 6. Let's reduce that and get 1 over 3. Make sure you understand what 1 over 3 means. Pause the video for a second and think about what this number represents. Well, 1 is our shadow location, so our distance from the pole, and 3 is our flag height. This is our independent variable. So as we raise the flag height, for every 3 feet that we raise that flag height, the shadow moves away from the pole 1 foot at a time. So what about our rule? Well, our rules are typically written in linear function form, y equals mx plus b. The plus b represents our starting point, but according to this graph, we're starting at 0. So we can just use y equals mx as our rule. And m represents our rate of change for every x unit that we move. And we know that we are going to change 1/3 for every x unit. In other words, our shadow will move 1 foot from the pole for every 3 feet we move in height. Now that we have a rule, we can use this as well as the graph to answer some questions. Here's our rule. Y equals 1/3 x. Question 1. What shadow location would you predict when the flag height is 12 feet? That's an easy one to use our graph for. I would just go here to 12 feet, go up, find this point, and I could determine that the answer would be 4 feet. But what about the next one? What shadow location would you predict when the flag height is 25 feet? 25 is not on our graph. This is 22, and it looks like it's around 7, a little over 7. So what do you think it's going to be at 25? You might predict 8, but this is where we can use our equation to help us with our predictions. Well, the flag height, remember, is our x, or our independent variable. So all I need to do is use my equation and replace the x with 25. If it's easier for you, think of 25 as 25 over 1. And then I just multiply across. 25 over 3. But this doesn't mean a lot. If we think back to the question, it asks what the shadow location is if the flag height is 25 feet. If I said the shadow location was 25 over 3, you wouldn't know what I was talking about. So we need to divide this out and get 8 1/3. Now I can better answer this question and say that the shadow location would be somewhere between 8 and 9 feet. Let's look at the next one, letter C, or the third one here. What flag height would locate the flag shadow 6.5 feet from the base of the pole? This one we can answer from the graph. If the flag shadow is 6.5 feet from the base of the pole, that's about right here on our graph. So if I come across, I can see that that hits the line about right here, right around 20 feet. The final one. By now you should be able to pause the video and see if you can answer the question for yourself. What flag height would locate the flag shadow 10 feet from the base of the pole? Well, 10 feet's on our graph, but if I go across, I never hit the line. So in this case, we'll probably need to use our equation. But the question is, where do we put the 10? You have to be careful to make sure you put it in the right variable so that you get the right answer. What does the 10 feet represent? The given is the flag shadow. The flag shadow is our y variable. That's given. So in our equation this time, we would need to put the 10 in place of the y, not the x. But what we're trying to find is the x. We're trying to find the flag height, which is our x. How can we solve this for x? Remember that we either divide by the coefficient or multiply by the reciprocal. In this case, since we have a fraction, it makes more sense to multiply by a reciprocal. So what is the reciprocal of 1/3? Well, we just flip it around and we end up multiplying by 3 over 1. Therefore, we need to multiply the left side by 3 over 1 as well. 3 times 10 is 30. 10 is the same thing as 10 over 1, and 1 times 1 is 1, so we can just leave that off. On the right side, 3 times 1 is 3, and then on the bottom, 1 times 3 is also 3. Look what happens here on the right side. 3 divided by 3 is just 1, so those cancel and we're left with 1x, or just x. Now we can answer the question. For a flag height of 30 feet, we know that the flag shadow will be about 10 feet from the base of the pole. Notice that if I come out here and look, here's 20. I would probably have to go out pretty far to make an estimate from the graph. So using a rule really helps us to make predictions. And that concludes our lesson from today on fitting lines. Now you can understand that linear patterns can be modeled by linear functions. You can fit a line to a near linear pattern and find a rule, and then use that to help you make predictions.